Now we will move to another very important application of the Reynolds transport theorem, which is the energy application. So again, going back to the Reynolds transport theorem, but now we will replace our beta variable by the specific energy E, which represents the energy per unit mass, which is equal to the summation of internal energy. So this is the internal energy, which is related to the energy of the particles, of the molecules. We have the kinetic energy, which will be induced when we have motion of particles. And we have the third type is the potential energy, G. So we might have other types of energies, let's say electromagnetic or electrostatic, but in the majority of our application in fluid flows, these are the main type of energies involved. So now what will happen if you apply the Reynolds transport theorem to the specific energy E, which is the energy per unit mass? What will happen is that we'll obtain the first law of thermodynamics applied on a certain control volume. In fact, let us see how the terms will appear. So first, we know that from Reynolds transport theorem, when we apply on our control volume, we'll obtain the following relation. First, the variation of energy of the system. So you know that Reynolds transport theorem will relate variation of energy in the system, which is the control mass, to the variation of energy in the control volume, and the fluxes that are crossing the control surface. Okay, so first, if we do the interpretation of dE by dt for a system, you know that the energy variation for a system can happen in two main ways, or in form of energy or in form of work. Okay, so if I have Q dot dE by dt of a system can be written as summation, if you want, of Q dot minus summation of W dot. And what do we mean by this? Q dot is the transfer of energy in form of heat. Okay, so if you gain heat or you lose heat, this is in form of energy. Okay, so we have transfer of energy in form of heat. So if this is related, you know, to in general variation in temperature, or sometimes you can have heat transfers that is latent. So if you remember, when you have change in phase, you can have constant temperature, but you will have transfer of heat in latent form. So whenever I move, let's say, from liquid to gas, if I have evaporation, let's say, so I can have exchange of heat at T constant, for example. This is possible. Okay. Or if I am in one phase, so if I am in the liquid phase or in the gas phase, then transfer of heat will lead to variation in temperature. Okay, so we can have energy transfer in heat form, in latent, or in sensible form. Now the other type of transfer of energy is in form of work. Okay, so you have you know that we can have work of forces, and this work of forces will lead to a certain energy, because we know energy variation, because we know that energy, for example, energy, if you recall from dynamics, is defined as force times displacement. Okay, so I can define the work and energy have the same units, both. So when I talk about energy, it can be expressed as energy in form of heat or energy in form of work. The unit of energy is joule. Okay, so work has the same dimension of energy. It's in joule. So one form of energy exchange will be through work, and another form will be through heat transfer, which is represented by Q. So the work has the same unit of energy. And now if I want to see the variation, the rate of work with time, dW by dt, or W dot, then its unit will be in watt, which is the unit of power. Okay, you know that power is expressed as the derivative of work with respect to time. So the power definition is dW by dt, and the corresponding unit is, so if you derive here, let's say, you know that the derivative of a distance, when you derive a distance with respect to time, you will obtain velocity. This is why in dynamics, if you recall, the power can be calculated as force dot V. Okay, so here what we will have that when you apply the conservation of energy on our system, when we apply the Reynolds transport theorem on the specific energy, what will happen is that dE by dt of the system, which represents the total change in energy of the system, will be through or heat transfer, okay, Q dot, or is related to power, which is the rate of work. Now, if I represent my control volume, let's say, I can say that my system will exchange energy due to transfer in terms of heat or in terms of rate of work or power. So, and the convention used here for the sign is the following. We consider that if heat is gained by the system, I will consider it as positive. While if heat is lost by the system, it's considered as negative. So Q out is considered as a negative flux, while Q dot in is considered as a positive flux. The convention for work, for rate of work, is different. You have some books that will put for you plus W dot, but then the conventions that are considering will be opposite. Here we are working with the following convention, that we consider a work or the rate of work as positive when it is produced by the system, because we, in this convention, we say that for me it's a productive system if it's generating work. This is why in the following convention, when we put minus, work, the rate of work is considered positive when produced by the system, while if I should put work on the system, then I'm considering that I will lose work because I will put it on the system, so I will consider it as negative. So this is a convention. The importance is that you understand which convention you are using. If you are considering the convention here, that when the system is producing work, I will consider it as negative and as positive. And when I put work on it, I will consider it as negative, then I should put the negative sign. However, if you say I will consider that everything entering the system is positive and everything getting outside of my system is negative, then you will put the convention plus. And both at the end will give you the same result. The importance is that you understand when I use minus here, then the rate of work that is going out is positive and the rate of work that is coming in is negative. Okay, while if I use plus here, then everything coming in is positive and everything going out is negative. Now we will work with this convention because it's used a lot in thermodynamics. So the majority of thermodynamics books work with this convention. So we can say that the variation of energy of the system is simply the balance of transfer in form of heat and in form of power. Okay, and now using the Reynolds transport theorem, we'll see this will be equal to what? So we will relate the variation of energy in the system to the variation of energy in the control volume, which is valid by just applying the Reynolds transport theorem. So now, let us see what we will obtain. So dE by dt of the system can be replaced by the rate of energy and work, okay, which should be equal to the transient term of energy variation throughout the control volume, which is del by del T integral of the control volume. If you remember, in the Reynolds transport theorem, you have beta here. So now I am applying Reynolds transport theorem for the specific energy E. So all I have to do is to replace beta by E. So integral over the control volume of E rho dV plus integral over the control surface of E times rho times V dot dA. So here again, we replace beta by E, okay? And V dot dA is equivalent to V dot the normal vector, unit vector to the area, times dA. Now, let us see for each term what we will obtain. So now we will do analysis of these terms to know what is this, by what we will replace this term and by what we will replace the following. Okay. Now, considering W dot, it represents, as we said, the rate of work for the system, and the work can be divided into several parts. I can consider shaft work. So if you have a compressor, let's say, or a turbine, you have the shaft work. You have the work of pressure forces, which is called W normal. You have the rate of work of shear forces, which are in general frictional forces, and you might have any other source of work. Okay, and here again, for our applications, when we consider, let's say, compressors, turbines, and pipes. So in general, the three main types of rate of work will be shear, normal, and shaft work. Okay, so these are the three terms that we'll consider in our study. So now, let us do analysis of a very important component, which is the work of pressure forces. And we will see that this term can be combined with the integral over the control surface. We'll see how. Okay. So if you recall, when we talk about work of pressure forces, okay, how to find the rate of work of pressure forces, we have seen together that the rate of work is a power, and power is force times velocity. Okay, so if I consider any surface, and this surface is subjected to pressure forces, and I want to determine the rate of work of pressure forces, all I have to do is to take the pressure forces and multiply them by the velocity. And since this is a dot product application, so the power is defined as F dot product of V. Okay, so I can replace this expression by, when I replace the velocity vector by V dot n. Okay, so I will end up with the following, that since the pressure force is always a compressive force, so I have minus P times, I will replace V vector by V dot n. Okay, so I will have that by minus V dot n, because let's say here, as you can see here, if I consider the following surface, and this is n. Okay, so if I'm considering velocity at an inlet, I should put, for velocity vector, which is opposing n, I should put minus V dot n. So for an inlet, I get that the dW dot P is minus P times minus V dot n dA. And then what I will obtain, if I want to take the total term over the control surface, when I do the expression of the total term over the control surface, I'll obtain the following. I can replace the term, the total pressure work in terms of over the control surface as integral over the control surface of P times V dot N dA. Okay, so what can I deduce then? I can deduce that the work of pressure forces can be calculated as an integral term over my control surface. And this expression is valid for inlet and outlets because V dot N will change in sign if it's inlet or outlet. And we know that the term for inlet is opposite to the term for outlet. Okay, so this is the general term that can give me the total rate of work on a control surface. And if I go back to my expression, I can replace then the total rate of work by the rate of work if I have a shaft, so if it's the case of a compressor or a turbine, plus integral over the control surface of P times V dot NdA. Now, similarly, for the shear stress also, by analogy, by same approach, I know that the shear is applied on the control surface also, but it's along, it's not perpendicular to the control surface. It's in this case along the parallel to the surface. This is why also to find the total rate of work of shear forces, I should do integral over the control surface of tau dot V. So I will do this along the stream surface, so parallel to the surface. So this term will be integrating over the control surface the shear, and this term will be integrating the effect of pressure forces. And now, if I go back to my Reynolds transport theorem, okay, my Reynolds transport theorem will take into consideration work of all forces, shaft rate of work, the W dot V represents, this is the viscous effect, so due to shear forces. So this is the rate of work for viscous forces. And as you can see, we have taken the term of pressure, which is the rate of work of pressure, to the other side. You know why we have taken it to the other side? Because in the other side, okay, we have also we have the term integral over control surface of E times V dot N dA. So we have in common, we have seen that we have in common this term. V dot N dA is common between the term of energy over the control surface and the term of work, because we have seen that the rate of work is given by the following expression. It's integral over the control surface of P times V dot N dA. Since we have a common term between both, so we'll take this term into factor, and then we will end up with, here we have rho times E, and here we have P. So if we take into factor V dot N dA, then we will have the following. We'll have integral over the control surface. Okay, so since we have minus W dot P, since we have W dot P as the following term, taking it to the other side, okay, we'll have the following. We'll have integral over the control surface of P plus rho E times V dot N dA. So because these two terms have something in common, we will group them together. So we will group them together in one term, okay? And we will see what is the advantage of doing this. So going back to my expression, so here, before taking it to the other side, we had here minus W dot P, okay? So now when you take it to the other side of the equation, it will become plus W dot P. And then if you take, as we said, if you take into factor V dot NdA, you will obtain rho E plus P. Here I have taken rho into factor. So you get into brackets a very important term, which is E plus P over rho. And you know what? Now, if you replace E by its expression, if you recall, E represents the energy of any molecule, and this energy is decomposed into internal energy plus kinetic energy plus potential energy. Okay, and now if I add to it plus P over rho, when you add plus P over rho, you can have you will have this term U plus P over rho. And in thermodynamics, this is a very important property. In thermodynamics, U plus P over rho is called the enthalpy. And you have tables, thermodynamic tables, which will give you how the enthalpy will vary with temperature and how it will vary with pressure. So our enthalpy is a property that we can find values in tables. This is why, for convenience here, we will replace E plus P over rho by H, which is the enthalpy term. So now, how our equation, what is the final expression of our equation? This is the final expression of our energy equation. Q dot, which represents the total heat transfer, okay, minus work, rate of work produced by a shaft, minus rate of work produced by viscous forces, is equal to del over del T of integral over the control volume of the energy term. So here, in case you have a transient application, in case you have an accumulation of energy in your control volume, this term will not be zero. So if you have accumulation of energy or loss of energy in your control volume, you should take into consideration this term. Plus, you have the integral over the control surface of the enthalpy plus the term of kinetic energy, so plus half V squared, plus the term related to potential energy times rho V dot N dx. Now, maybe this equation might seem a little bit complex, but now we will see that for our applications, it will be much easier. Okay, so let us see how we can apply it in specific cases. So first, again, in majority of applications, we deal with 1D uniform inlet and outputs. So if we have this case, then the equation can be transformed into the following. It's Q dot minus W dot is the variation of the transient energy variation for the control volume plus summation of fluxes of energy that are coming in minus summation of fluxes of energy that are going out. And for steady application, what will happen? This term will cancel out. So if I have a steady flow with uniform single inlet and single outlet, then my equation will be Q dot minus W dot is. Now, look what will happen here. If we just apply our formula, if you go back to your formula, you have P over rho plus internal energy. So here you have plus rho U plus P plus rho V squared over 2 plus rho G. Because we said that this is rho times H, the enthalpy, okay? But sometimes in a lot of applications, the internal energy, okay, is not varying through the flow. So for example, in general, the internal energy is function of temperature. So if you have large variation in temperature, then your internal energy will vary. So H is defined, as we have seen, as U plus P over rho, okay? In general, if I don't have a large increase in temperature, so if T is nearly constant, then I can say that the variation of internal energy with my cross sections is not will not have a change of internal energy. Or if I have negligible variation of temperature, so for small delta T also, if I have a fluid moving, and of course I'm talking about a single phase, I don't have change in phase, because when you have change in phase at constant temperature, you can have variation of internal energy. But if I'm talking about flow of water, so I'll always have water, I don't have transformation into vapor. Then if I have small delta T or if I have nearly constant temperature, I can neglect delta U variation, okay? So then I can simplify, instead of dealing with enthalpy, which is U plus P over rho, I can just say that the enthalpy term can be neglected, okay? And I will just work with this term, which is P over rho. So if you replace H by P over rho in the equation, you will get the following. You will get that Q dot minus W is equal. Now, because we are dealing with uniform single inlet and outlets, if you remember, as we did for the continuity equation, when you integrate, okay, v dot n is constant, then I can take it outside of the integration, and I will obtain the following. I will obtain that the mass flow rate m dot over rho times p plus rho v square over 2 plus rho gz at the outlet minus m dot over rho times p plus rho v square over 2 plus rho gz over the inlet. So I can deduce that the variation of the net rate, if you want, of heat and work is equal to what is going out minus what is coming in. Okay, so and this is valid because when you consider here, if you take any system, okay, but here just we should pay attention for signs. Here it should be minus, and here it should be plus. Okay, why? Because look, whenever you have a system, you have what is coming in and what is getting out of your system. You have fluxes. Okay, you have fluxes of heat that are crossing your system. Okay, so you have that the change of energy within your system will be equal to the variation of to the balance of fluxes of energy coming in and going out. Okay, so what will happen here, for example, let us take an example. If I consider an application where I have, let's say, a pump, a turbine. Okay, so what will happen then? For a pump, the pump will provide work. So when we talk about a pump, the pump will deliver work to my system. Okay, so it will deliver work to my system. Then since it's putting work on my system, okay, since the pump is putting work on my system, then I can consider, if I follow my convention, if I follow the convention we are working on, when I put work on a system, then it's considered as negative. So I should put minus W dot pump. Okay. Now, for a turbine is producing work. A turbine is producing work. It's delivering work out of the system. Okay. So then if I deal with the turbine, I put plus W dot turbine. Okay. And in case I have, let's say, viscous forces, then they will I will lose energy. So whenever I have friction, what will happen? When I have friction, then I will, if you want, I will lose energy. Okay, I will lose energy, and or I can consider that the work of these forces will take energy from the system. Okay, so then